Good day, class. In this lesson, we will learn to solve exponential equations. Let's take a look at our first example. Here we're asked to solve 3 raised to the x is equal to 81. So if we employ the laws of exponents and the properties that we know about logarithms, then we'll know that we can rewrite 81 in terms of base 3. So 3 raised to the 4th power has the same value as 81. And we also see that the only way that these two can be equal, 3 to some unknown equal to 3 to the 4, is if x is 4. There's no other possible value of x that could make 3 to the 4th except 4. So in this case, we know that our unknown value of x is 4. Now, with that being said, let's continue with other examples. Here we have 2 raised to the 2x is equal to 8. Okay, well, we can do the same with that 8 because 8 can be written in terms of a base of 2 raised to some power. So if we do that again, then we can see that 2 raised to the 2x is equal to 2 raised to the 3 only if we can somehow get that 2 times x to have a value of 3. So we show them to be equal. So 2x equals 3 simply means divide both sides by 2, and we have x is 3 halves. So the solution to our original equation is 3 halves. The unknown value of x has to be 3 halves. In our next example, we have 5 raised to the 4x minus 7 is equal to 125. Again, if we can just write 125 in terms of having a base of 5 raised to some power, then we can get this thing solved. So here we can rewrite 125, very familiar value, as 5 raised to the 3rd power. So now 5 raised to the 3rd power can be written, can now draw out a conclusion of 4x minus 7 equals 3 because those two sides of our equation have same basis of 5. So their exponents therefore must be equal. And of course we can solve this very basic equation where 4x minus 7 is equal to 3 means that 4x is equal to 10 if we add 7 to both sides. And then of course if we divide by 4, we discover that x is 10/4 or x is 5 halves. Now, this example is slightly different because I'm looking at 2 raised to the x power equals 33, and I want to rewrite 33 raised to some, as 2 raised to some power, but I don't know what power I can raise 2 in order to get a value of 33. So it doesn't work out so well in this case in terms of rewriting a number in a new base. And so now I decide then to take the log of both sides because the properties of logarithms allow me to do that. If I take the log of 2 raised to the x and the log of 33, then I'm keeping my equation in balance because I'm taking the log of both sides of the equation. So nothing has changed. I'm just doing something, performing an action on both sides of the equation. Once I do that, I can employ the laws associated with logarithms by pulling that unknown out of the sky, or that exponent, I should say, out of the sky, if you will. And so now I have x times log 2 equals log 33. And if you respect that log 2 is a constant value, then you'll know it behaves just like a coefficient of x. And you can divide both sides of this equation by log 2 in order to get x by itself. So now we have x all by itself, and then we have its value is equal to log of 33 divided by log of 2, which is a constant value. Now, your calculator can handle that for you. There were times where we would use extensive computation, or we would use a scale, and they call them log tables and various resources. But for the sake of what we're doing in this course, we're going to use our calculators to compute log of 33 divided by log of 2. So I need you to do that, and then recognize that your result is going to be an irrational number. And so that number will have to be rounded. And so once you round it, you have an approximate value instead of an exact value. So approximate value, 2 raised to 5.0444 is 33. And so that's an approximation. Now, whatever you get in your calculator is exact because it is your calculator is able to draw that out to a conclusion that your double check methods will understand. But once you round it, you have an estimation. In this example, we're given e raised to the t is 1,000. So again, we can't really switch the bases here. There's nothing much we can do with that except rely on the properties, in this case, of the natural log. So we're going to go with ln because, and you'll see the beauty of this in just a minute, but whenever we see that e raised to the t, or we're dealing with the number e, remember the number e is actually a constant, but when we're dealing with the number e, then we enact the properties of natural logs. And so ln e of t is equal to ln, or ln e raised to the t is equal to ln of 1,000. And so we're taking the natural log of both sides, and then we can pull that t down out of the sky. That's the beauty of using the properties of these natural logs. And so now we recognize that the natural log of e is just 1. And that's beautiful. And so we receive that and we use it to our advantage. We're now on the left-hand side of this equation, we just have t times 1, or just plain old t. And then our calculators can handle the natural log of 1,000. And so we'll have t is approximately 6.9078. Please take this time to continue on to part 2, since there are several more examples that you may want to see before you begin your practice.